Hello guys, welcome back to the Riscv channel, a channel for embedded Rust programming on RISC-V. So this session is about writing an embedded Rust system level code for UART driver on RISC-V based FE310 SoC. Okay, so this session briefly depends on one of my previous session about a modular HAL driver for GPIO. So if you haven't watched, I highly recommend you to watch the suggested video above before getting into or before starting with this one. Okay. So first and foremost, before we get into the UART driver code, just want to mention about a few Rust specific features like the how we do compile with a conditional flag like hash if definitely there is an equivalent in Rust, but it's a bit different. So I would just touch upon the conditional compilation in Rust and followed by how to create how to configure the configuration file, project configuration file or the create configuration file to have multiple binaries, but only one library. So Rust allows uh, the project or the crate to have multiple binary crates, and but that can have only one library crate. Okay, so these are a few things I just want to touch upon before getting into the UART driver code. So the TOML file, let's so this is the code from the Git repo. Few changes I might not have submitted it, but right after this session, it should be available in the Git repo. So in the TOML file, uh, if you see here, so whatever is mentioned as library, that would be compiled as a library, whereas anything with this, which is marked as a binary, would be compiled into a binary. So in this TOML file, as you see, I have two binary files. I'm generating two binaries. One is the LED blink code. Before, this is the only one application that I had before, but right now I just want to create another application for UART1 loopback. So that's when I figured that out. There is a way, and so all this, whatever I say, if you read the Rust language ebook, then the documentation on Rust is very clear and everything is available online. And so what? So if you see here, so that is the one library with the name FE310. So whatever is there as part of this lib.rs, and if you go to the lib.rs, I have two modules. One is the GPIO, which I had before, and I have created another module for UART, and this is the uh, what is that? The as usual, I created a raw pointer with the memory map address of the UART and wrote methods with those structures. Okay, so in the TOML, so this lib.rs and the lib.rs has two modules. So all this would be compiled as a library, whereas for the when on the binary side, so whatever is there inside the source.bin would be compiled as part of the binary. Since I have mentioned two separate binaries and I have given the path inside the binary directory, which Rust files should be compiled as LED blink and which one should be compiled as UART1 loopback. And regarding the conditional compilation, there is something called as features, and you have to set default features, which are all like so. Here I have created two. One is UART and GPIO. And if you go to the modules, uh, .rs, so if this feature flag or if GPIO is enabled, then this module would be compiled and used. Similarly, if UART is defined and used or set in the feature flag here, then it would be compiled. So the default by default, I have enabled both the UART and GPIO. So both this would be compiled. Okay, and why I need both for UART, we will soon see that. Okay, so that's on the conditional compilation and creating this multiple binaries with one library. Now coming to the UART loopback, first I started writing this code just to transmit and try to grab the or probe the UART TX pin by sending just 10 bytes, and I'm able to see that on the TX pin the data has been transmitted properly. Then once that is done, um, I'm just gonna run the loopback, just connect a wire back from the UART1 TX to the RX and see if the data transmitted is received back. So that's the exercise as part of the session. But a gentle note here, if you see the schematics of the FE310 or the Hi-Fi 1 revision B board, so you would see the numbers on the J2 jumper with running from 1 to 8, whereas on the board those silk screen numbers run from 0 to 7. Okay, so now let's jump into the code. So this is the UART1 loopback binary, or the entry point for the UART1 loopback binary, and this is the UART module or the driver code. So this definition is almost like a same how I did for GPIO. So these structure format is, or this order is same as what is mentioned in the FE310 manual. Then I create a tuple struct in Rust with the mutable um, raw pointer for the structure, and there are two instances of UART in FE310. So I have just created enums. It prevents passing incorrect instances. So for instance 0, so this is the raw pointer address, and for instance 1, and this is address. So this come from the manual, or that FE310 manual. So for what instance 0, this is the address, and if you see the registers format or the order, this is what exactly you would see that same here. Okay, and a couple of more enums. One is because the UART in FE310 supports both 1 and 2 stop bits, and the baud rate a lot more is supported, but right now I'm just trying to run at 115200 baud rate. Okay, so I have created a init method to get the raw pointer or RUS, then set the baud rate, set number of stop bits, and FIFO size. It supports from I think 0 so up to maximum of 7 or 8 FIFO. Let's see the FIFO size. Yeah, depth is 8. Okay, so maximum of 8 FIFO depth you can set. So it would take in a value from 0 to 7. And if the value is out of range, this just panics. Otherwise, it sets the FIFO size, RX FIFO size, and then enables the UART method to enable UARTX channel, another method to enable RX channel, then a method to transmit the data and to receive a data. And also I have written a method to check if the TX FIFO is full. So if the TX FIFO is full, any writes into that TX transmit register would be just dropped. At the same time, if the RX FIFO is empty, if you read, then you will not have any, you will not be able to read any valid data. So the read should be performed only when the RX FIFO is not empty, and write should be performed only when the TX FIFO is not full. Okay, so these are all the methods, and now on the application. So very first, these two pins are all like the GPIO 18 and 23. So 18 and 23 are multiplexed. So it can be used as a GPIO or as an UART 1 TX and RX pins. So that's why this application needs both GPIO and UART, because very first, once we set the stack, trap handler, and clear external, and these are all similar to the GPIO application, then it has to configure those pins as an IO functionality rather than GPIO. Then select the IO functionality, which is UART here. So 0 means if you go through the manual here, what is a GPIO? So this is how the schematic of each GPIO pin is. And if you go down, yeah, so IO functionality. So GPIO 23 and 18, if you see 18, so if the IO functionality is enabled instead of GPIO, then if the select IO of select register is written as 0, then this pin would be working as UART1TX. Same for a GPIO 23. So that's this code, and then creating an UART with instance 1 and set the baud rate to 115200. And I have a TX buffer, and this data has been carefully filled so that it would be on the, if I probe the TX pin, it would be very easy to check on the waveform, because for one, that should be just 1 bit duration of raised level, and for 3 that should be 2, and for 7 3, and here it should be 4. And so it would be easy to compare in the waveform if this is right or wrong, if this data is transmitted properly or not. Okay, so let me start capturing now and then run here, because stop, I'm just transmitting. Let's see here, I can stop this. So this buffer is just transmitting 10 bytes. So that's why I have to enable the capture before the transmission starts. So that's like 1, 2, 3, 4, 5, 6, 7, 8, 9. Why it's 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just transmitting only 9. So, oh yeah, right. Okay, so 0 to 8. So it's just transmitting 9 bytes. So the reason why, now if you see the waveform, so this would be 1 because in UART transmission, the LSB is sent first. So if you see here, this is 1 followed by 7 zeros. Okay, now if you go to the next, so this is like, so approximately with the 115200, each bit is approximately 8 microsecond. So this is like 2 bits. So 1, 1, and rest are all zeros. And this is the LSB. So this is 3. So this is the reason is now it's easy to compare and check if this data transmitted is right or wrong. So this should be for approximately 3 bits because this is 7. So 3 eights are close to 24. Okay. Now it should be 4 bits, approximately 32 microsecond. Yeah. So that's pretty much about the transmission. Now this transmitting the data and probing on the TX pin works well. So next is the loopback. Now let's loop back the wires and run and see if we receive the data and store back into the RX buffer the same what are the data we transmit if you are able to receive it and write into the RX buffer. So I have initialized this RX buffer with this a sequence of numbers so that it is initialized with these, and when we read these bytes and write back, we should be able to see this change so that the TX buff and RX buff should be the same. Okay. Now I would just write the receive code or the code to receive the data, whatever is transmitted. Then I would just loop back the UARTX to RX pin. So the receive code should go here. Receive. So once the index, just in case if index goes beyond 9, I would just set it back to x equal to 9. So we don't need the parenthesis in Rust. So xidx equal to 0. Same. Dx equal to, just reinitializing just in case if this index overflows. Bullseye. Gargoyle build. It's 1, 2, 3, 4. Load. And okay. So right now, yeah, insert stack these two variables are not yet in scope. So let me run up to, so with the object dump, we can get the address of those symbols. And I just want to run up to transmit. Let me see, where is that? What? Set board. Okay, let me give a breakpoint here. X. Let me run up to that and see what is that. Right now it's inside the transmit function. Step, step. Okay. So now the TX buffer and RX buffer should be in scope. Let's see. Yep. And RX buff. So as I said, so right now this buffer have these values. Okay, let's run now. Okay, delete the breakpoint and run. Control C. So this code, after transmitting those 10 bytes, 9 bytes, there's an infinite loop. So it will be just looping around here. And let's see if txbuff and rxbuff, yeah, so the 9 values, whatever we transmitted, those are received into the rxbuff. So that's pretty much about the UART. We are able to successfully transmit and receive data. Okay, and see you in the next session. Thank you.